You might wonder how the squeeze theorem would apply to examples in mathematical biology. There aren't a lot of examples, but a really cool one is high-frequency ventilation. Now, high-frequency ventilation is used to ventilate lungs when they're easily damaged. This could be, for example, in premature babies. And the machine helps gas exchange by producing very low amplitude, high frequency, i.e. short wavelength pressure waves. And this allows for gas exchange in the lungs, even though the frequency is super high. Indeed, the wavelength can be as short as 1/10 of a second. Normally, we just breathe a few times per minute. So 1/10 of a second is super high frequency. So we call the wavelength mu squared. This is the Greek letter mu that we're using. A simple formula for the pressure then is P0 plus A times sine 2 pi T naught over mu squared. And so this is the pressure at any given time, T naught, which is measured in seconds. And P naught is the background pressure, which turns out to be about 10 centimeters of water. That's how it's measured. And it's a mean airway pressure. And what we're interested in is what happens to the pressure as the wavelength goes to zero. So we want to consider the high frequency limit. Mu approaches zero. So to keep the energy of the wave constant, we have to relate the amplitude A to the wavelength. And what we need is that the amplitude to be proportional to the wavelength. So we write A is equal to A naught times mu squared. And we choose A to be 20 centimeters of H2O per second as our parameter. When we put all of this together, this gives P of mu is equal to 10 plus 20 times mu squared times the sine of 2 pi T naught over mu squared. And then we can ask ourselves, what is the pressure as mu goes to zero? This is the high frequency limit. To answer this question, we can use the squeeze theorem. And let's just consider this part right here to start. Okay? So consider mu squared sine pi T naught over mu squared. And we know that a sine function has to lie between -1 and 1. We have -1 is less than or equal to the sine is less than or equal to 1. And so we choose the upper function, h of mu is equal to mu squared. And we choose the lower function, f of mu is equal to minus mu squared. And so the limit as mu goes to 0, h of mu is equal to the limit as mu goes to 0 of f of mu is equal to 0. We call this function g of mu. So this implies the limit as mu goes to 0, g of mu is equal to 0. So finally, the limit as mu goes to 0, p of mu is equal to 10 plus 20 times the limit as mu goes to 0, p of mu, which is equal to 10. And so in the high frequency limit, the pressure goes to the background pressure, which in our example was 10 centimeters of H2O. So this is kind of interesting because energy is still being put into the system. In fact, we chose the relationship between the amplitude and the frequency so as to keep the energy constant. However, the pressure approaches a constant, P naught, in our case 10 centimeters of H2O, in the limit as the frequency gets very high. And it's by this method that the high frequency ventilation prevents damage to the lungs. There is very little change in the actual pressure, but the rate of ventilation is very high, and this is enough to mix the gases in the lungs to allow for carbon dioxide transfer and expelling the carbon dioxide. And so this is one of those things that if you're in a prenatal ward, you'll often see being used.